Welcome back. So, remember we want to look at pressure in fluids, right? This is I guess you can say the bulk of this unit is about pressure in fluids. The previous video we looked at density and pressure, the basics of it. So do you remember what the formulas are for those two? Density, we use rho equals to m over v. Wow, my rho is very big. Then for pressure, we looked at how pressure is related to force and area. Force over area. So we're going to combine those two ideas now to talk about pressure in fluids. Depends a bit on density, depends a bit on pressure. And then, yes, eventually we'll go to upthrust force. So let's take a look on what pressure in fluids is all about. So what is pressure in fluids? Here I have a container of water. Okay, just let's think about water because we can see that every day in our water bottles, in our bathrooms and things like that. What's causing this water to stay in the container? Why doesn't it float somewhere else? Think about it. In space, if you have a container of water, the water will just float. But on Earth, you have what we call a gravitational force pulling every single water H2O down. So all the H2O are being pulled downwards. So what happens is, all these water molecules are actually exerting some kind of force on the container. Okay, so let me try to draw it out as well as I can. So all these arrows, it's like all the forces that these molecules are exerting all over on the container. So not only it exerts on the container, if you put something inside there, the water molecule is also pressing on it. Okay, press, 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 press. Basically, throughout the whole fluid, you will have forces going on because water molecules getting pulled down by gravity and they're all squashing each other. Okay, if you have object, like if you're swimming in the pool, you have all these tiny little red arrows all squashing you everywhere. Why is that? Because water wants to go down because it is pulled by gravity down, so they all want to press down. So think about this. We talk about pulling down, press down, all this stuff. Where do you think the water pressure is the greatest in this container? Is the pressure the greatest here or here at the bottom? Think about it. Now if you think about, oh, pressure is stuff pressing on you. If you want to think about water pressing on you only, if you're at the top, so up here, there's barely any water pressing on you, so pressure is lower up there compared to right at the bottom where you have the whole column of water squashing down on you. So pressure changes with height or depth. I'll use height here, height of water on top of you. So that's why if you get a water bottle or can, you poke holes, then you see the water that come out, you will see something like this. Because the pressure increases with depth, so down here is high pressure, then up there is lower pressure. So low pressure means it will force the water out slower. Then here in between, then down there, wow, very high pressure. So all the water gets forced out, pushed out through this tiny little thing. It's kind of like when you go to the toilet and you pee. If your bladder is very full, then you're like, wow, then you push very high pressure, then your pee will come out very far, very far and very fast. Similar idea. Pressure, things like that. At A levels, we won't need to calculate this water fountain thing. Okay, it's actually a projectile motion if you think about it. Anyway, we don't have to worry about that. All you need to know is that pressure changes with depth. Okay, so we have depth, and we have, what else do you think will affect pressure? So what affects pressure? We have depth, H, or whatever, D, whatever you want to use it. I use H lah. We have gravity. We talked about gravity. If you're on another planet where the gravity is very, very, very big, then it will try to pull all the H2O molecules down even more. Then the pressure at the bottom will be even more. Okay. What else? What else? Imagine you're swimming. So like this fella, swimming. You're swimming in a swimming pool. Then you swim in the ocean. Then you swim in a... What else can you swim in? In the mud. I don't know how you even breathe. But you swim in the mud. tank and you dive to the bottom, the pressure is actually different. You will feel it because if you have ever gone swimming before, you dive to the bottom, you feel like your ears very pain. You need to do something to regulate the pressure. So that pain is because of all the water on top of you pressing down on you. So what's the difference between water, seawater, and oil or mud? Density. So pressure is something to do with density of the fluid itself. Ooh. So before we look at what the equation is, let's take a look at some simulations to get a better understanding of what pressure in fluids is like before we look at the equations. So this first simulation in GeoGebra is about fluid pressure in two containers. If you want to try out the simulation, the link for the simulation is down in the description below. So please go try out, play with it so you can understand it better. So let's look at this part on the left. Okay, they're both identical, exactly the same setting. So they're the same now, huh? So look at the left. We have some familiar stuff here. Pressure is force over area. Force of what, Force of 4.02. So look here, the 4.02 is the weight of this whole column of fluid pressing down on something, okay? So what they're calculating here, P1, is how heavy is this thing, what weight, pressing down on an area at the bottom. So 50.27 times 10 negative 4, so that's here. So this P1, what they're calculating is, what's the pressure at the bottom here because of this column of water squashing on it. What if we change the height? I can drag this up and down. Notice how the weight changes, okay? So less water means less weight, lor. Less weight means lesser stuff pressing on you. So here you have 231 Pascal, 200, lesser and lesser water pressing, so less water, less pressure. Height is related to how much water there is in this case. Okay, so this is how you can change the height of water and change the pressure. Now what if we change the area? What if I make this container more slim? What do you think will change? Area, of course, will change. What, the pressure? Let's take a look. So now it's 800 Pascal. What if I make it slim? Oh, doesn't change all. Why is that? Yes, I'm making the area smaller, but there's also less water in this simulation lah. If the same height but smaller area, still the same pressure at the bottom. Now in real life, you may be thinking, oh yeah lor, if you squash this container, shouldn't the height go up because the water gets squashed ma? Yes, in real life that is the case. So okay, in real life, let's say you have this little water, then suddenly you squash it, then the water will go up. So in that sense, yes, the pressure will increase. But for this simulation, you see the height never change. This is a not real world one lah. So let's go back to our original radius and height. Last thing on top you can change is density of fluid. Make a prediction. If I make this density higher, what's going to happen to this pressure? Increase or decrease? So here's how you think of it. Density increase means this water will be heavier, so more water to press on the bottom. So let's see. Wow! Almost double. So back to 1000. Okay, so 1000 pressure is 800. If I double to 2000 density kilograms per meter cube, wow, your pressure also double. Because density times 2, your weight also times 2. Weight times 2 means your F here times 2. F here times 2 means everything also times 2. So times 2 times 2 times 2, everything become double. So that's how you can play with it. Okay, you can compare different heights, different densities, okay, and you can see how to make sense of pressure, height, density, area, and what else? Weight, mass, all these things. So we're going to use all these ideas all put together, all the things you can change, density, force, area, height, and we're going to create an equation which allows you to very easily count the pressure. See here, they kind of do for you lah, but it's in a few steps. They count weight and then they use the weight, find mg and things like that. So next up, we will look at how we can derive an equation based on all these ideas put together in one. Let's revisit the container we looked at earlier and use that as our baseline. Okay, so I'm going to put some labels on it. Let's say the height of this water column is h. Okay, that's the amount of water pressing down on the bottom. Cross-section area, let's call it A for now. Pi r square and things like that. And we're trying to find what is the pressure exerted by this column of water on that level at the bottom from that height. Okay, so our water will have some mass, some density, and things like that. But most importantly, I want you to remember that it has some weight to it. Heavy gravity pulling it down. And weight, we know is mg. So the mass of the water times gravity. What if we don't have the mass of water? We only have the density. We know water's density because it's fixed Oh, so remember density is mass over volume. Okay, what other things we need to remember? How does force and pressure relate? Pressure, big P, force per unit area. Okay, anything we need to remember? I think this is most of it. Yep, I think we're good. Okay, so we are ready to start the derivation. First step, we're going to think about how this water, or the water above that point, let's say the bottom is where our reference is now. So we have some force equals to mg. Where is mg come from? Oh, because of weight. Here, weight is the force that's pulling all the water down. So force equals to mg. That's the force exerted by this whole clunk of water. Then mass. If we don't have the mass, no panic. We can just use density times the volume of the water. So rho Vg. There. So actually, I can just stop there and say, hey, the force exerted by this amount of water at a certain level down there is rho Vg. Okay, but it's not quite the final form we want yet. Let's expand a little bit. So force, based on this one top here, force is pressure times area. So let's sub that in. So force is pressure, area, rho Vg. We want an equation for pressure. So we need to rearrange a bit. So let's say pressure is rho Vg over A. Okay, almost done. Wait, can simplify some more. Volume and area, how are they related for this cylinder thing? Actually, not only for cylinder, for cubes, for blocks, all kinds of normal shapes. So the volume is actually the cross-section area times the height. Okay, think about that. Volume is the cross-section area times how high it is. So the height. Yeah, there we go. So I can simplify some more to get rho, volume is area times height. We can cancel out the area. So area and area is gone, which gives us the final form of the equation, which is the pressure at any point in a fluid is because of is related to the density of the fluid pressing on it, the gravitational force, which planet are you on, and how much water is on top of you. So this one is the one for you to remember. We use the word hydrostatic. You may see this word before. Hydrostatic does not necessarily mean water but you can use for fluids. Fluids including air, including water, including molten lava. So fluids, not just water only. You have air, you have water, you have molten. Molten means you heat up, let's say molten iron. Heat up the iron, is so hot it becomes like a fluid. Same thing, okay? So just remember this. You need to know how to derive this equation because in paper 2, or sometimes in paper one, they will ask you, show how you get this. Then you have to go through all the steps here, how you sub, what you sub, and how you transform it into this final form. So remember, you need to know how to derive it, and you'll be good for this hydrostatic pressure. So now, let's take a look at a diver. Based on this equation, how we can think of people diving and things like that. In this short and sweet question, you can see, we're going to look at the same container, but what if there's a tiny little block inside? How would the forces look like? Remember just now I draw red arrows, but that one not draw properly one. Here's how we can think about how to draw it properly. So you have a mini block in a container of water. Which diagram correctly shows the possible situations as viewed from the side? So here, we view it from the side, and all the arrows are how? How do we draw the arrows? Think about it. Pause the video and choose before you continue, because I want you to think about how are you currently thinking and how you can improve. Okay, so let's try to remember a little bit what the principles are like. Now remember, the forces, or I should say pressure, increases with depth. So the deeper you go in the container, the bigger your arrows should be. Okay, so deeper means larger force, I should say, larger arrows lah. Okay, so firstly, yes, there will be some liquid on top pressing on this container, but the liquid at the bottom pressing up should be bigger than those on top. So we check through the answers. The bottom one is all bigger than top? Yes, okay, so all good. What about the sides? Now the sides also have arrows, so B is out for sure already. But how do the arrows change? Let's look at the difference between all of them. A and C, the side arrows are going from small to big. Oh, because as you go deeper, the pressure is bigger, so that's correct. But D, hey, your arrows are all the same. No, no, no. Pressure it should increase with depth, so your arrow should get bigger and bigger. Now let's start between A and C. The difference is just the arrows. So how? Here's how we can think of it. At the top, the pressure is almost the same. So your arrow should be about the same length lah. So here should be roughly the same. That's too long, that's too long. So at the side, near the top, pressure is still roughly the same. So it should be roughly the same arrows. Then you slowly get bigger and bigger until it is almost the same length as the one on the bottom. So the most likely choice in this case is A. Because if you look at C, this means the pressure here is smaller than the pressure on top here. Cannot be. Cannot be, cannot be, cannot be, cannot be. They should be quite similar, not so much smaller. Something's not right. Okay, so not C. So all that's left is A. So remember, whenever you see arrows like this, think about some key points. First key point is, let's use green. How about that? The arrows on top are smaller than the arrows on the bottom. And this is always true because gravity is always pulling everything down. So down there, the pressure is higher than the pressure on top. The next one is pressure on the left and right. At the same level, every level, this pressure is the same as the pressure here. Because pressure is the same. Sorry, not this pressure. The force along the same level is the same. Left and right, left and right, left and right, on an object. So here means this arrow and this arrow is the same. Pressure must be same in the same depth. So those are the two key points you need to remember, top, down, left, right, how to think about pressure. Okay, over here we have back to GeoGebra, another simulation. Link is also down below in the description. So here we have a fun diver trying to go scuba diving. Okay, so I can drag the diver around. Ooh. Notice how at this moment the pressure P gauge is 0 Pascal. What do you mean by 0? What is gauge? Gauge means it's a type of device you can measure relative to some point. So if I say the pressure up here is 0, means as I go down, the pressure will increase. Okay, so that's what it means. It says this sea level is 0. In some systems, you will see, well, I'll show you later, where the sea level pressure, absolute pressure, is actually not 0. But for now, for gauge pressure, pressure is 0. Okay, so as we dive down, we look how the pressure will increase because there's more water pressing on top. So see, note how the gauge pressure is increasing as you go down. So let's say at the bottom here, wow, the ear is very painful already, 15 meters below water. What if I change the shape of the reservoir with this thing here? Do you think the pressure will change if I make this whole tank smaller? Let's check and see. Dun 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 dun. Oi, pressure never change. Doesn't care what the shape is. So that the reason why is because this, you only care about the column of water above this diver. That is the one causing the pressure. Everything else, the other side there, you don't care lah. You only care what's on this part here. Okay, so I wonder what happens if I do this. Oh, it doesn't change also. Okay, so the main idea is the shape doesn't matter. It's just what height or what depth is the diver below water, below sea level. Now let's look at this. What if we change the water level? Less and less water pressing on the person. So you see the pressure is going down. Okay, so that is what will change the pressure, not the shape of this water reservoir. And also, this is in the swimming pool. So if you change the density here, wow, your pressure also increase because you're going to sea. Okay, so let's go back to water because it's a nice number, 1000. Whatever lah. 1002. Oh, I can just do that. Nice. Okay, one thing I want you to be careful of is absolute pressure. Sometimes you will see people talk about it as atmospheric pressure or things like that. So what that means is, let's bring this person to the top. Here the gauge pressure is 0. But if I show absolute pressure, there's a way to measure it with a barometer. Okay, that's how you spell barometer. Absolute pressure is actually 100,000 in this case. Oh, why got pressure up there? Don't forget, let me put this down a bit so there's more space up there. Don't forget, there's also air on top of this sea that's pressing on the person. So the atmospheric pressure also is a pressure. So if you want to look at absolute pressure, then at this surface, you already have 1,000. Wait, not 1,000, 100,000 pascals pressing on you. So if you go down, you will increase pressure because now you have air and water pressing on you. So that is what we call absolute pressure. Or if you want to think of it, later we'll look at a term called atmospheric pressure as well. Notice how the equation is different. Here got extra P0. P0 is just pressure at sea level. So sea level. We usually assume pressure at sea level to be the same worldwide when we're doing calculations. So remember, difference is gauge pressure is just, we say here what sea level is 0. So from there on, how much pressure? Absolute pressure is, you want to take into account the air pressure, atmospheric pressure up there also. So when you draw graphs, you need to be careful. If you see a graph like this, where it's just pressure and it starts at 0, means you're looking at gauge pressure, where sea level is 0. It's the kind of like relative pressure like almost. But if you see a graph that looks something like this, where there's an intercept, then you need to be careful and think about, oh, atmospheric pressure, absolute pressure. This is a graph of absolute pressure and not just relative gauge pressure. So be careful when you look at graphs. One of the paper 2 questions have graphs like this and they ask you to explain why is that intercept there. So that's all I want to show you about this simulation. Make sure you go try it out, play with it, and have fun. So I hope that those simulations were helpful in helping you to see how things changed. Highly recommend, go try it out. Anyway, so we're going to look at a bunch of questions now, about 3 or 4 of them. to help you familiarize with the style of past year questions, especially in MCQs, because MCQs are so tricky. So here, we're back to the swimming pool. We have a diagram, cross-section of an Olympic-sized swimming pool with water. Diagram not drawn to scale. Okay, good to know. The density of water is 1,000 kilograms per meters cubed. And what is the difference in pressure between X and Y? Where is X and Y? Take a look. Okay, if you want to try this out on a piece of paper as well, you are welcome to. If you have the handout, that's on page 29. Pause the video and see if you can figure out what the pressure difference is between point X, which is right at the bottom, and point Y, which is somewhere here. Okay, go try it out. So one thing to note is they want pressure difference, not just pressure. So there's going to be some pressure at Y, and there's going to be some pressure down here at X. You just need to find the difference in pressure. So difference in pressure is basically Px minus Py or something like that. So I'm going to show you the long way and I'm going to show you a shortcut. Kind of like a shortcut. Actually, let's just go to the shortcut. Let's do that. Okay, so you want to find pressure difference. That's Px minus Py. So pressure at X will be rho g h x minus rho g h y. Okay, so far so good. So pressure X means you have this column of water, this height of water pressing on you. So 2.35. Then at Y, you will have this height of water pressing on you, which is 2 meters. But we can factorize a little bit. We just have hx minus hy, so height of the water above, which then you can just simplify to be rho g, change in height. That's it, lor. So you need to find the change in height is, oh, that's a very small diagram, is this little red thing here, this height. Okay, from Y to X, how much is that? So the change in height, we can calculate to be 2.35 minus 2 meters only. A very small change in height, just 0.35 meters. So then you can just calculate the change in pressure is density 1,000, 9.81 times change in height 0.35 meters. So you should get about 3.4 kilopascals as your change in pressure. The other way, the longer way to do it, which I didn't do, is to find Px separately, Py separately, and then you minus both to find the difference in pressure. You can do that too, but I'm going to use a shortcut, so I play around with the equation first, then only I plug in all the values. So this is an example of a pool. Let's look at the next one. This one I call pressure ratio because they didn't exactly give us values to calculate. What to do? So let's see. Liquid Q is twice the density of liquid R. At depth X in liquid R, the pressure due to the liquid is 4 kilopascal. At what depth in liquid Q is the pressure due to the liquid's 7 kilopascal? Wow. For me, if I read so many words like this, my brain also a bit jammed. So let's draw pictures. No picture, must draw picture to help us out. So let's see. Let's draw two containers lah. Assume this first container is liquid Q with some water inside. Yeah, why my water disappear? Then we have liquid R inside another container. So things to note. Liquid Q has twice the density of liquid R. So Q is 2 times more dense than R. In other words, we can say the density of Q is 2 times the density of R. So far so good? Okay, we're just changing words into equations to help us later on. Okay, info they give to us. Depth X in R, pressure is 4 kilopascal. So maybe I say X is somewhere here from the top. Okay, this is X. At that depth, the pressure is 4 kilopascal. So 4 times 10 to the 3 Pascal. You know, to save space, I just won't write Pascal. You know it's Pascal lah. And then for Q, at what depth? We are trying to find that. What depth is the pressure 7 kilopascal? So somewhere in this liquid, you will have 7 kilopascal. And I don't know what depth is it. I'll just call it D. From the surface lah, depth. So how do we, what do we do? Don't panic, stay calm. All you need to do is think about the hydrostatic pressure equation first. So P equals to rho GH. For Q, we know that at that certain depth, we're trying to find what that is, we have density of Q times G times that depth. We know that already, it's given to us. For R, if we do the same thing, P is rho GH, we know that 4 times 10 to the negative 3 equals to the density of density of R times the gravitational constant times X in this case. So what next? We're trying to find D. So you look on the left side, we're trying to find D here. Let me circle it. We're trying to find D, but we don't know density of Q. But we have another equation on the right side, and we can relate both by how their densities are related. So, interesting. Let's try it out. Let me rearrange a bit. For the right side, let me sub in a density of Q. So we write 4 times 10 power 3 equals to, density of R is half density of Q times G times X. Now I can do simultaneous equation, sub rho Q into rho Q. You know, let me do it this way. So rearrange a bit. Rho Q is 2 times 4 times 10 to the 3 divided by G times X. Then I plug this whole thing into the other equation on the left side. So now 7 times 10 to the 3 equals to rho Q. We found the rho Q. Rho Q was 8 times 10 to the 3 over G times X. Then GD, that's all that's left. Now I can rearrange everything. Oh, G and G cancel out. I just need to find what is the depth D, because everything nicely cancels out. So I have my values, I can use my calculator. So if you calculate, you should get about, give me a second, 7 times 10 to the 3 divided by 8 times 10 to the 3, 7 over 8x. So this is the answer already, 7 over 8x. What we just did was we used ratios. We didn't have values to plug in, but we used ratios here, especially to connect two different scenarios and solve it. So this is what we call solving algebraically. Sometimes they will throw you algebraic questions like this, where they don't give you values to count, but you need to play around with equations. Let's look at another one where you actually have values to plug in. This one, fluid rocks, I call it, because it's so cool when you think about it. Okay, let's read the question. The maximum pressure that granite rock can withstand is 2 times 10 to the 8. Okay, above this pressure, your rock begins to flow like a liquid. The density of granite is that given. What will be the height of a granite mountain whose base is beginning to flow? Let's draw a picture of this cool scenario. So if you have like a mountain, if the mountain is too high, it's going to exert some pressure at the base of the mountain, right? And if the pressure here is too big, then the rock will become a liquid. Or like a fluid lah, I should not say liquid. Shh. The rock will become a fluid and then it starts to flow because the pressure is so big, it press ma. Oh wow, that's so cool. So how do we solve this? It would be wise to draw a column, because you draw a mountain like that, a bit hard to imagine what's happening. So let's draw a column. Let's say this is one slice of the mountain. Okay, slice like that. So we're trying to find the pressure at the bottom and what height of this mountain is before the rock down there start to become fluid and flow down here. Okay, so we look at the hydrostatic pressure. P is rho GH. Now we're going to use not absolute pressure lah, so we say the pressure up here is 0. Save us extra calculations. Okay, maximum pressure that the rock can stand. We want to reach this because past max already, then it's beginning to flow ma. So we'll say what is the height where the pressure down here will be 2 times 10 to the 8. Okay, so 2 times 10 to the 8 equals to density of granite 2.7 times 10 to the 3 times gravitational constant times the height. Let's find the height. So plug in the height, check what you get. 2 times 10 to the 8, 2.7 divided by 9.81. So you will have about 7550.874 blah 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 blah. You can just shorten it to say 7.6 times 10 to the 3 meters. So that's how you can say, oh, if your height is 7.6 times 10 to the 7.6 kilometers, then the bottom pressure will be reaching the maximum limit and it's going to start to become fluid. So your rocks start flowing. Wow, this is so cool. Okay, so we looked at liquid, we looked at rocks that can become fluids. The last one we're going to look at is air, gases. And now the last question, atmospheric pressure, finally. Okay, this one, compulsory, I want you to pause the video and go try it out first. If you want to try it out on the book, the handout, it's on page 30. If you don't have the handout, that's okay. Go online, find the past year question and try it out, or just grab paper and look at the question. So pause the video, try it out. Because this one, most people will usually get it wrong on the first try because there are some traps or some misconceptions that we have. But if you don't try, then you don't know what misconceptions you have. So try it. It's okay to get it wrong. Pause and come back and we'll look at it. Okay, so if we look at the question, the first thing we have is, oh my goodness, there's so many words. How to make sense of this? So, like physics, classic, draw a picture. I'm going to take a slice of the earth, atmosphere and the water. This is a slice of the earth, so there's water, there's earth. Okay, first problem we have. You have a density that's changing. 1.22 and then 0.74. How? Because of sea level, the density of your air is 0.77. 1.22. But then as you go higher, suddenly your density becomes so thin. This is the problem with gases. Their density keep changing. So, how to deal with this problem? Firstly, let's find the average density because it will make calculation easier. So, average density will be 1.22 plus 0.74. So, about 0.98. Let's use that for our calculations. Okay, what info do we have? Atmospheric pressure on a day, it changes day by day, hot day, cold day, is 100,000, which means Earth's surface we usually call sea level. So I'm going to use, say, this here is 100,000 pascals at sea level. The value of G between Earth's surface and altitude can be roughly 9.7. So don't use 9.81 if they give you 9.7 already. What is the atmospheric pressure? Atmospheric pressure at an altitude of 5,000. So atmospheric pressure at 5,000 means from the sea level you go up. Sea level is 0 meter. 5,000 will be somewhere here. And I ask you, what is atmospheric pressure at 5,000? Okay, so quick note, if you see Earth's surface pressure of 100,000, that means all the air on top pressing down at this level will cause a pressure of 100,000. That's just what it means. Okay, let me rub off this extra mess. So if we're trying to find the atmospheric pressure at 500 meters, means all the air on top, how much is pressing down? We don't really know how high the thing goes or what's the maximum height, so that's a problem. Anyway, here's how we can solve it. What if we find what is the pressure from this column alone? Okay, because of this 5,000 meter of air, what is the pressure down here? That one we know how to do because we've been doing that lah. So column of air, height is 5,000. What is the pressure here? So we do pressure is rho GH. So density, we take the average within that column because it keeps changing. So 0.98 times the height, 5,000. So what we get? Rho G. Forgot the G. 9.7. 0.98 times 5,000 times 9.7. 47530 Pascal. So this 47530 is the pressure here because of all this pressing down. So we have found the pressure because of all this pressing down. But we want the pressure up here. So this is not the answer that we're looking for. So this is what we want. So what you could do is you minus off some things. So we know that the pressure of the entire air column is 100,000 pascals. And we know that because of this column of air, the pressure pressing down is 47530. So we're trying to find what is this pressure here at this height. Atmospheric pressure lah. So what you can do is you take 100,000, your P here will be 100,000 minus what we just found, so 47530, which will then give us 52470. So 52470. That will be the answer for us. The answer round up to 52,000. So this is the part where people often get trapped. You need to understand what pressure are you finding. Our equation that we use normally, the rho GH one, this one, rho GH, is just the pressure because of a height of air on top of us. But what we want is not that. What we want is the red color one. So you have to minus off, okay? Think of it as finding pressure above, and things like that. So just remember, air is a little bit more tricky. If you see atmospheric pressure, you want to draw a diagram like this and think about everything carefully. Okay, atmospheric pressure is everything above pressing down. So that's all I have for you for pressure in fluids. Remember, fluid can be air, water, rocks that flow like a fluid also can. The next class, we will look at the last bit on upthrust, very short one. And then, actually we'll have a bonus to come back to this atmospheric pressure thing. It's a bonus chapter for pressure in pipes and tubes. So hang on for that. Alright, so that's all for today.